Hello everyone watching this video. In previous video, we discussed the moment of inertia for a ring, and in this video, we will discuss and derive the formula for moment of inertia for a disk. And first, we take the moment of inertia for a disk about an axis perpendicular to the plane and passing through its center. But before that, we will get through the difference between a ring and a disk. Here, you can see this is a ring and this is a disk. It's a CD which we use in the computer. So this is the ring in which the mass is distributed over the edge, or we can say at the circumference only. But in the disk, mass is distributed continuously in the entire disk. And in the disk, we first are taking the moment of inertia for a disk about an axis perpendicular to the plane and passing through its center. So our axis will be according to this marker. So this is the disk and this is the plane of the disk, and this axis is perpendicular to the plane of the disk and passing through its center. So we draw the diagram here, and this is the disk and is the axis, and this is passing through its center. So here it is the diagram of this disk and its axis which is passing through its center and perpendicular to the plane. So here about this axis we will determine the moment of inertia in first case. So we will follow all the steps that which we followed for the moment of inertia for the ring, in which we first take a small component or a small mass component, because our formula for moment of inertia is I equals to integration dm r square. So we need dm over here. So for the disk we need a component. For the ring we took a component of small circumference, but in the ring its mass is distributed continuously. So we can assume that this disk is made of different rings of different radius. We can assume that this disk is made of different rings. So for the mass component, for the small component, we assume a disk of radius is small x, and we assume that thickness of this disk is small ring component is dx, and we assume also that mass of this complete disk is m and radius of this disk is capital R, and the radius of this small component, ring component, is small x, and thickness of this ring component is dx. So first we need to determine the dm for this integration. So dm for the dm, first we need to dm, we can write say first for the dm we first determine the density. So all the complete mass of this disk is distributed over its area. So first we determine its density, or we can say the areal density, which is m upon pi r square. In the entire pi r square it contains mass m. So in per unit area the mass of the disk is m upon pi r square. So it is the areal density for this disk. And here we have the area of this small component, which is 2 pi x into dx. 2 pi x, it is the length of this small component, and dx is the thickness of this small component. So its area of this small component is dx. Then the mass of this small component will be density into area. So the small mass will be density into 2 pi x dx. Now we will put this value in this formula and we will derive the formula for moment of inertia. So I will be integration sigma 2 pi x and dx. Here the distance of the small component from the axis is small x. So we take x square. So we solve this, we take all the constant out from this integration like 2 pi sigma, and x square and x will be become x cube and dx. And here value of x vary from 0 to capital R. So we use the limits of integration from 0 to capital R. Now we will integrate this 2 pi sigma. Integration of x cube is x power 4 upon 4, and here the limit capital R. When we solve, we put the upper limit, that will be r power 4 upon 4, minus when we put the lower limit, that will be 0. So I will be 2 pi sigma r power 4 by 4. We can put the value of sigma now, that is area density I equals to 2 pi. Value of sigma is capital M upon pi r square, here r power 4 upon 4. We cancel it by 2, r square cancel out by square, pi will be cancelled out, and the I4 or moment of inertia for a disk about an axis perpendicular to the plane and passing through it, its center is mr square by 2. Previously we determined the moment of inertia in the same case for a ring, that was mr square, but for the disk it is mr square by 2. It's just half of the moment of inertia for the ring. It is just half because this mass is distributed from axis to at this distance, but in the ring this mass is distributed over the circumference only. So this is the first case in which we got the I mr square by 2. Now we will take the reference cases is we took for the ring. You can write down these and make the notes for the revision purpose. So we take a different axis now, about an axis along diameter. For the diameter, we draw the disc here, and now this disc and the axis that we write here, that is along the diameter and passing through its center. And for this we just discussed in the last video that we use the perpendicular axis theorem. For that we draw one more axis. These two axes are perpendicular to each other. We say moment of inertia about this axis I1, moment of inertia this axis equals to I2, and the moment of inertia of axis perpendicular to the both of the axes is IZ, and we can draw it completely. Now, according to perpendicular axis theorem, IZ equals to I1 plus I2, and here I1 and I2 both are equal axes. So I1 equals to I2, and we can write equals to I. So we can say IZ equals to 2I, and here I will be IZ by 2, and I will be value of IZ that we determined just in first case, the moment of inertia of disk about an axis perpendicular to the plane and passing through its center, which was mr square by 2, and here this 2 is here. So moment of inertia about an axis along the diameter will be mr square upon 4, just half of the moment of inertia about this axis. So here we completed the second case and we move to the third case, and third case is moment of inertia about an axis along the tangent, For this we have to remove it, and We draw the axis and disk. Here our disk, and mass of this disk is capital M, radius capital R, and here the axis. This axis is a long x tangent, and here we use the parallel axis theorem. And for parallel axis theorem, we need a axis parallel to it, about which we know the moment of inertia, and that is here, along the diameter. This axis is parallel to this axis, and at the distance between these two parallel axes are capital R. And here we know moment of inertia about this axis I naught equals to mr square by 4, and we need to determine the moment of inertia about this axis. And according to parallel axis theorem, I equals to I naught plus mr square. So I will be I naught, value of I naught is mr square by 4, and the mass and square of distance is mr square. When we get the value of I is 5 by 4 mr square. This is the moment of inertia for this disk along an axis along the tangent. So this is our third case, and now we take the fourth case and then we wind up our video because length is going too long, and this is a very big problem to upload this video of big length. So that's why we have to control the length of the video, so we don't waste any time and we move forward. The moment of inertia for the disk about an axis along the perpendicular tangent. Perpendicular tangent, but do you understand? So here, this is our disk and this is the axis, because you can assume the marker as an axis. So this is the axis, this is the axis along the tangent. When I put this ring here and I use this pen as an axis, then you can see this is the axis along perpendicular tangent. It is a tangent, but it is perpendicular to the plane of the disk. So this is the disk, axis along perpendicular tangent. So here we also use, to determine the moment of inertia along this axis, we also use the parallel axis theorem, and parallel axis theorem says we need another parallel axis to this axis, and here we have another parallel axis, the I naught. In first case we determined the moment of inertia for this axis, which was mr square by 2 for a disk of mass capital M and radius capital R. So here, according to parallel axis theorem, I equals to I naught plus m d square, and distance between two parallel axes is capital R. So I will be I naught, value of I naught is mr square by 2 plus capital M, mass of the disk, and the distance between two parallel axes is r square. So moment of inertia for a disk about an axis along perpendicular tangent is 3 by 2 mr square. So there, today we derived 4 formulas. Please make the notes for the revision purpose and solve all the numericals from your textbook examples or from textbook examples and previous questions. And we complete this video today here, and we move forward in the next video. Thank you very much.